In the last lecture, we have discussed in detail the architecture and organization of 8051. Today, we shall introduce to you its instruction set, and so that you can write programs and ultimately build systems comprising both hardware and software. The first important parameter is the data types that is supported by the processor of the 8051. As you know, the 8051 is inherently a 8-bit processor. Since it is an 8-bit processor, obviously the ALU and the registers are of 8-bit. And since the ALU is of 8-bit, it can perform all the arithmetic and logical operations on 8-bit data. But in addition to this 8-bit data type, it can also perform several other data types, for example, bit manipulation. I have mentioned earlier that bit manipulation instructions are very important in the context of microcontrollers, because it has to perform various control operations, set, reset, and it has to read a particular bit from the IO port, set a particular IO port, reset a particular IO port, and so on. So bit manipulation instructions form a very important part of the microcontrollers. So 8051 supports bit manipulation in a big way. That means it can perform on 1-bit data, and we have seen that a part of the RAM, part of the data RAM, that is your from 20 to 27 internal RAM locations, which are bit addressables. That means from, and they can be addressed as 00 to 7F. So 00 to 7F, these bits, these 16 bytes are available in terms of bits, and each of these bits can be accessed. And similarly, some of these registers like A, B, interrupt enable, interrupt priority, all the 4 ports P0 to P3, then serial port controller, the timer controller, all these registers which are known as special function registers, they are also bit addressable. And the various types of bit manipulations that can be done are, for example, you can perform set, clear, complement, and also various types of decisions can be taken, like jump, if clear, if set, and so on. We shall later on discuss about it, and I have mentioned about it in my last lecture. So it can support 1-bit data type, and a number of instructions are available which operates on a subset of the internal data RAM and also a subset of the special function registers. Okay. Then it can also perform on nibble data. Nibble means here the data is of 4-bit. So it can perform operation on 4-bit data. However, instead of performing arithmetic and logical operations on 4-bit data, primarily it does exchange of 4-bit data. That means lower order nibble can be exchanged with the lower order nibble of a register can be exchanged with the lower order nibble of some memory location, particularly internal data RAM or some other register. So we can say that data type, that 4-bit data type is also supported. Moreover, we shall also see that it can support double byte. That means it can perform operation of 16-bit, and particularly you can transfer data in terms of 16-bit, and we shall see, of course, whenever you are performing, say, multiplication, division, then multiplication, particularly result will be of double byte, and you can transfer double byte data to some registers like program counter, you can transfer data to data pointer and so on. So we can say that the 8051 not only supports 8-bit data type, it supports beat, nibble and double byte. So that is the first important parameter. Next is the instruction format. What kind of instruction format it supports? And we have already seen the need for an instruction format. Unless the instructions have well-defined format, the control unit of the processor cannot detect or cannot identify or process efficiently. In other words, the controller will be very complex if the format is not well defined. So to reduce the complexity of the control unit, it is necessary to have well defined format, and 8051 has a restricted instruction format. Particularly it can be 1 byte. A majority of the instructions are of 1 byte, and there are 49 instructions which are of 1 byte. So byte type. Then there are of course several instructions which are of 2 byte. For example, you have to, whenever you have to provide immediate data and so on, in such cases you will require 2 byte. So in this particular, whenever it is byte type, it will be like this. There will be 8 bits, B0 to B7. That means this is the lower order bit and this is the higher order bit. This is the little endian convention that is being used in case of 8051, and in case of 2 byte instruction, the there will be opcode. In this case, it is in case of byte, it is opcode. Of course, in that opcode itself, part of the opcode can represent some register that we have seen in case of 8051. Here also, part of the opcode can be used to address a register. So in case of register addressing, it can be done. On the other hand, in case of 2 byte data, there are 2 bytes opcode followed by another byte that can be some data or some other information. Usually it is data, immediate data or something else. Then the number of 2 byte instructions are 45, not very small. Then there are few instructions which are also of 3 byte. That means here you have got opcode followed by 2 bytes. These 2 bytes can be usually data, immediate data. When you have to load the data pointer, which is a 16-bit register, this has to be of 16-bit. And number of 3 byte instructions are 17. Now, you may be asking why you are interested to have lesser number of single byte instructions rather than 3 byte instructions. The reason for that is that execution time is directly related to the size of the instruction. Shorter the size of the instruction, lesser is the execution time. And in case of 8051, as we have seen, the instructions can be executed in 8 cycles. 8 cycles. So you will see that the total number of instructions which can be executed in one machine cycle is 64. Although you have single, I mean 1 byte instructions of 85, there are few instructions which are of double byte can be executed in one machine cycle. How? Let me explain little bit. So here, for example, we have seen that this is a single machine cycle comprising 6 states: S1, S2, S3, S4, S5 and S6. And internally, this clock, which is available on XTL crystal 2 pin, is divided by 2 to generate non-overlapping 2-phase clock, which of course are not visible to us. That's why I have drawn only the clock which is available on this pin, crystal 2. However, internally this is divided, converted into 2-phase non-overlapping clocks, and this is phase 1 and phase 2. This is phase 1, this is phase 2, phase 1, phase 2 and so on. and they are numbered in this way. This is S1 P1, this is S1 P2, this is S2 P1, S2 P2, and so on. Now, as I was telling, how you execute some of the 2-byte instructions in a single cycle. That is possible because you are generating two ALE signal with the help of which you can read 2 bytes of code from the program memory in a single machine cycle. So you can see here S1 P2 and S2 P1. During this period, one ALE signal is generated. Similarly, during S4 P2 and S5 P1, another ALE is generated. So first byte of opcode can be read with the help of this ALE. Second byte of opcode can be read. That opcode that is from the program memory can be read. It can be data. It can be read during this second ALE. That's why it is possible to execute some of the instructions which are of 2 bytes in a single machine cycle. That's why the total number of instructions which can be executed in a single cycle is 64, and if you add up the total number of instructions is about 111. That's a nice number to remember. So the 8051 provides you 111 instructions, out of which 64 can be executed in only one cycle. So you can see here a good number is executed in one machine cycle. However, 45 instructions will require 2 machine cycle. And there are few instructions like multiply and divide, which will require 4 machine cycles, and that number is 2. So this is your instruction format. The number of instruction formats supported is 3: single byte, 2 byte, and 3 byte, and we have seen how the execution time is related to it and how many instructions require how much time. Now let us focus on the second important parameter, that is the addressing modes. The 8051 supports 5 distinct addressing modes. These addressing modes are register addressing, second one is direct addressing, then you have got your register indirect addressing, then it supports immediate addressing, and finally there is another very interesting addressing mode, that is a combination of base register plus index register indirect addressing. So you can see here in this case you are using a base register. The content of base register is added with the content of index register, and then that provides the indirect address. So these are the 5 addressing modes supported by 8051. Let us consider in detail each of them. First is the register addressing. In case of register addressing, the registers which can be addressed by their symbolic names, there are various registers that you have seen inside the processor. The registers are, first of all, you have got these general purpose registers available in 4 banks, and each bank is having 8 registers. These registers are accessible by the symbolic names R0 to R7, but as I have already told you, at a particular instant only registers of one bank is available, and which particular bank is available, that is decided by this program status word register. Depending on the value of this RS0 and RS1, that is your 0, 1, 2, 3, 4 bit. That means bit 3 and bit 4 bit of the program status word, it decides, depending on this value, it decides which particular bank can be accessed at a particular instant. And we have already seen that whenever you reset the processor, by default these two bits become 0. That means after you do the resetting, the registers which will be accessed is the bank 0. So the bank 0 registers will be accessed after resetting, but subsequently you can program this program status word to access any other bank. So the first the registers which will be used for register addressing are R7 to R0. So these are the general purpose registers which can be accessed. Then you have got other special purpose registers, A, B, and various other registers are there. And in the register addressing, usually the register A, register B, and C, that this is your carry bit, which are used for bit manipulation instructions. As I have already told, this carry bit is used as some kind of accumulator in bit manipulation instructions. So for the Boolean processor, which is provided in your 8051, this carry bit is used as the accumulator. And A and B, as you know, A is the accumulator and B is commonly used for multiply and divide instructions. Whenever you do multiply, then one operand comes from A, another operand comes from B. So these two take part in register addressing, and can be used. B also can be used as general purpose scratchpad register when you are not using multiply or divide. Then apart from these registers, you can access A, B together as 2 byte. You can access them as 2 byte. You can load both of them together using a 2 byte register addressing. It is some kind of that register pair concept that you have seen in case of your 8085. There we have seen the concept of register pair. Here also AB is used as register pair on some occasions. Then there is another register which is also used in register addressing is data pointer, particularly whenever you perform double byte data. So these are the various registers which are used in register addressing. Later on we shall see instructions using these registers, using this particular registers. Now let us come to the second addressing mode, that is your direct addressing. In so far as direct addressing is concerned, the lower order 128 bytes of RAM, then special function registers, and 128 bit subset of special function registers of the address space are accessed with the help of direct addressing. Usually these two registers R1 and R2, R1 and R0, these two registers are used for direct addressing. And since these registers are of 8 bit, obviously your address space cannot be more than 256. That's why in this particular range you have got 128 byte of RAM. This RAM can be accessed by using direct addressing. Not only and not only in terms of bytes but in terms of bits. You can access this part of the RAM. So uh, direct addressing can be used for byte manipulation as well as for bit manipulation instructions. So and that is restricted to this RAM, and also the special function registers which are on the we have seen that the special function registers are also mapping from, say, from 00 to 7F is the uh, internal data RAM, and then 80 to FF, this is where your special function registers are mapped, and those special function registers addresses locations can be accessed by using indirect addressing. And also 128-bit subset of the special function registers, we have seen that some of the special function registers are available as in terms of bits. These registers, these registers are also accessed for bit manipulation instructions by using direct addressing. So direct addressing is performed with the help of these two registers, and usually this symbol is used whenever these two are used for direct addressing. Okay. Next addressing mode is the register indirect addressing mode. In register indirect addressing mode, you can access internal data RAM you can use the addressing, use those register R1 or R0. I am sorry, I have made a mistake here. Whenever you use direct addressing, this convention is, this symbol is not used. This is used for indirect addressing. So only R1 and R0, these are used for direct addressing, not at the rate. And only in case of indirect addressing, this at the rate is used. And so internal data RAM can be indirectly accessed with the help of this R1 and R0. And of course, in direct addressing, I mean, these not only these registers, all can be used, because those all the registers can be accessed by direct addressing, and only R1 and R0 and R1 is accessed with the help of indirect addressing. So R1, R0 and R1, with the help of which or the entire internal data RAM can be accessed, and also you can perform push, and by using the stack pointer you can also perform indirect addressing, and in that case you will perform push and pop operations. Then the least significant nibble of nibbles of internal data RAM can be accessed. Least significant here, whenever you are accessing, you can access in terms of bytes, and least significant data RAM can also be accessed in terms of nibbles. So in such a case also you will be using those registers R1 and R0 to provide the indirect address whenever you are performing nibble manipulation, 4 bits. So you can access 4-bit data of the internal data RAM. Obviously it is restricted to least significant nibble, or the 8-bit data when the entire byte is accessible, and in both cases R1 and R0 are used as the registers. Then you can also access the external data memory. We have seen that apart from the internal data memory, you have got the external data memory. External data memory can be also accessed with the help of these external data memory, that is your external to the chip, which is available from 0000 to FFFF. That also can be accessed. That size is quite big. Whenever it is within the 256, then you can use R1 or R0. But if it is you are accessing the beyond that 16-bit, then you have to use the data pointer. DPTR. So data pointer will provide the indirect address. So we see that with the help of this R0 and R1, you can access either the internal data RAM or the external data RAM, which is restricted to 256 bytes, or you can access the external data memory with the help of the data pointer, where it can be from 0000 to FFFF. The entire external memory can be accessed with the help of this data pointer. So the internal register indirect addressing mode will access in this manner. Later on we shall see the instruction utilizing these register indirect addressing. Then you have got immediate addressing. Immediate addressing is particularly used to read immediate data. As we know, whenever you are transferring some constant, then you have to use immediate data, and typical symbol used is this, and then you provide the data. So some immediate data can be loaded into the program with the help of this immediate mode of addressing, immediate addressing. Then comes the final addressing mode, that is your base register plus index register indirect addressing. In this case, the base register is usually the program counter or the data pointer. So program counter or data pointer acts as the base register, and the accumulator is used as index register in both the cases. So you will be adding the content of program counter with the accumulator, or the content of data pointer with the accumulator to generate the indirect address. So you can see here it provides you very wide flexibility. You can access memory by depending on the present value of the program counter or present value of the data pointer. You can do the indexing. You can increment or decrement the accumulator to access different parts of the memory by using this base register plus index register indirect addressing. Now, by using these various addressing modes, let's see what are the different types of instructions that can be implemented. What are the different types of operations that can be performed, instructions. If we look at the instruction set, the instruction set can be broadly divided into 4 different types. First one is known as data transfer. I shall discuss in detail what are the different types of data transfers that can be done and how they can be done. Then comes the second type, that is your logical. With the help of which you will perform various logical operations like set, clear, complement, AND operation, OR operation, exclusive operation, shift rotate operations. These are all logical operations. So you will be able to perform various logical operations, and logical operations can be done not only on byte data but also on bit data. So logical operations is extended to byte data, which will be performed whenever it is on byte data, it is performed with the help of the ALU provided as part of the 8051. When you are operating on bit data, there is a separate Boolean processor which will do these logical operations on bit data. Then you have got arithmetic operations. And arithmetic operations are obviously on 8-bit data. byte data, will be able to perform addition, subtraction, multiplication, division, compare, and so on. So later on we shall discuss about them in more detail. And finally, you will require control transfer instructions, with the help of which you will perform basically two types of jumps: unconditional jumps and conditional jumps. So they belong to the control transfer group. So these are the four different types of uh, instructions. So the instructions can be grouped under these four categories, and various instructions are available for data transfer, logical, arithmetic, and control transfer. Let us focus uh, on the data transfer instructions in more detail. So data transfer. Now the data transfer can be done from, say, program memory. Your program memory is, as you know, is ROM. Since it is a ROM, obviously you will be storing program instructions, but there are some situations where you can use it to store some important data, say table, a lookup table. A lookup table can be stored in the program memory, and you can read them. Obviously it will be only in the read only fashion. How you can do that? You can do that, of course in this case it will only go to register A, and the addressing mode that you can use is that PC plus A. So you can guess what addressing mode is being used here. You can also use that dptr plus A. That means you are using base register plus index register indirect addressing to perform lookup table from the program memory. And in such case, using these addressing modes, that means the base register plus index register indirect addressing, the table can be looked up where that accumulator will act as an index register. Whenever you are looking up a table, as you know, you require an index register. An index register has to be incremented or decremented to read a table. So here this accumulator performs that, and on the other hand, either the program counter or data pointer acts as the data pointer, and then that is added with the accumulator to generate the address, and you can access any part of memory starting from 00000 to FFFF of the program memory. You can also perform you can also read data from the external data memory. However, in this case your data memory is RAM. In the previous case it was ROM, so it was unidirectional. Data was coming only from the uh, from the uh, from the program counter, from the ROM, which is part of the program memory. Also, whenever you can read external data, you can transfer to the register A, in the same manner, and you can use uh, two addressing modes. One is your register indirect addressing mode. I mean, both are register indirect, and whenever it is you are using R0 and R1 for indirect addressing, obviously your memory is restricted to 00 to FF. That means 0 to 256 byte within that external memory. And whenever you are reading from the of bigger memory size, that means 00 to 0000 to say FFFF. In such a case, you have to use the data pointer as the uh, register for indirect addressing, and the corresponding codes for this particular case can be say uh, you can perform say move x. Whenever it is, the instruction will look like this: move x, then your at the rate ri, that can be ri, it can be r0 or r1, and a. This is the instruction that will be used. And for this one, the instruction will be like this: move x at the rate dptr a. This is the symbolic address. And whenever you are using transferring data from the program memory, the corresponding instruction will be like this: move c a comma at the rate a plus dptr, or it can be move c, that means code. C stands for code, symbolic names, and here x stands for external memory. A comma a comma it can be at the rate a plus pc. You have seen that it can be pc or dptr. So here we have seen that data transfer is taking place. Data transfer is taking place either from external I mean program memory, or from the external data memory, and the addressing modes used here is either in case of program memory it is base register plus index register command index indirect addressing, and here only indirect addressing is being used. Now let us come to another type of data transfer where this is your general purpose data transfer. General purpose data transfer is will take place to various registers of the selected bank, register A, or that carry flag bit where you will transfer bit. And here you see the data transfer will take place by using a variety of addressing modes, by direct mode, direct data, you can see it can be exchanged. It can be immediate data. Obviously, the immediate data is orthogonal in nature, only that immediate data is going to various registers by using register addressing or register indirect addressing, or by direct addressing, and also by immediate data can be transferred to the data pointer. You can also use register indirect addressing, where for stack pointer we shall see that push and pop operations, and you can use. So if we find that the data transfer to various registers of the register bank, the register A or register C can be performed by a variety of addressing modes, by immediate addressing, by direct addressing, by register indirect addressing. So these are the three different types of addressing modes which are used for data transfer to these registers, and we can see here whenever the data transfer takes place between the RAM and the registers, it is bidirectional in nature. That means it can go from register to the memory location data RAM, or for data RAM to the registers, except in case of immediate data. Now let us focus on this particular operation, push and pop. Push and pop operations can be performed, which is also some kind of data transfer, where the stack pointer is being used to provide the address. Let me write a simple program in assembly language, symbolic code. Move say dpl, data pointer low. I have used here this immediate addressing. You are transferring say 25, then another instruction I am transferring say another byte of data to lower order byte of the data pointer. Then suppose I have performed two push operations, and whenever I perform push operation I have to mention which particular register has to be pushed, say DPL and DPH. Let's assume we do that. So here it is H. Now let's assume this is the stack and you are performing initially the stack is initialized to stack pointer is 07. This is the initial value. We have seen that whenever you do the reset, the stack pointer is initialized with the value 07. So you see here stack pointer is essentially pointing to a location, a data RAM, which is part of the second bank, memory bank. That means this part can be, this memory bank is starting from say 07. That means whenever it is pointing to 07, starting from 08 you can store data by using stack addressing. That means this bank 1, starting from bank 1, this part of the data RAM, internal RAM, is used as stack. So the scratchpad register area can also be used as stack, since it is also accessible in terms of memory, data memory, and that is what is done initially. But if you want to use these register banks for some other purpose, obviously you have to initialize the stack pointer to point to some locations within the data RAM. If you don't do that, this will be used as stack. So whenever stack pointer value is 07, the data is stored in memory location 08, 09, 0A and so on. So this is initially. Now suppose you perform push, execute this instruction, push DPL. Then what will happen? The stack pointer will be incremented by 1, it will become 08, and what is the value there stored there? 25. So 25 will come to the memory location 08. Now if you perform another push, say DPH, then the stack pointer will be incremented by another 1 byte 09, and in the stack you will have here you have got 25, here you will have F3, this value which is already stored in data pointer higher order byte. So this is how the push and pop operation, push operations is performed. Now let us see how this is the illustration for push. Now let us consider how the pop operation is performed. Suppose you execute whenever this is the situation, initial condition is this. Here let's assume the initial condition is this, stack pointer is having the value 09, you have 2 bytes of data 25 and F3 stored in 08 and 09 memory location. Now suppose you perform pop 5. 5 means it is essentially telling about the register 5. So as you do execute this, what will happen? The stack pointer value will be decremented by 1, it will become 08, earlier it was incremented, and register that R5 will be loaded with the value F3. F3 will be loaded in register 5 and stack pointer will be decremented by this. Of course, here 25 and F3 will remain. Now suppose you perform another pop operation, pop 6. that means it goes to register 6, data will go to register 6, 25 F3, and this is your then it will become SP is equal to 07, back to the initial state, and 25 will be loaded, that R6 will be loaded by value F3. So this is how the push and pop operations are performed, and stack pointer provides the indirect address. And you can see here uh, in case of whenever you perform stack manipulation operations, you have to take care about the initializing the stack pointer. If you are not using bank 1, bank 2 or bank 3, no problem, you can go ahead with the whenever the power on reset is performed, it is initialized with 07. So in those locations the data will be stored whenever you push, and it will be read from there. On the other hand, if you are you are using those register banks, then you have to initialize with your desired value so that the register contents are not disturbed. So this is about the data transfer operations, general purpose data transfer operations. General purpose data transfer operations are taking place to internal memory and so on. The second type of data transfer operation is accumulator specific transfer. Accumulator specific transfers are taking place. So it is, these are essentially exchange instructions. As you can see, it is shown here, the exchange instructions given here. So exchange of data takes place. So exchange of data is taking place between register R0 of the selected bank and the accumulator. So you are exchanging data between a register and the accumulator, or you can exchange with direct data 40H. That means whatever was the value in the memory location 40H will come to the accumulator, and the content of the accumulator will go to the memory location 40H. That means within the processor. So this is the direct data transfer. This is the example of register in the register addressing, where exchange is taking place with a register, here with a memory location. And also you can do the exchange by using indirect addressing, where R0 or R1 can be used for register indirect addressing, and the data exchange can take place in terms of 8 bits or in terms of 4 bits. Whenever you are performing exchange of nibble, then the symbolic code is exchange D, and the registers that can be used can be R0 or R1. So these are the examples of accumulator specific data transfer that is taking place between registers, a pair of registers, particularly the general purpose register and the accumulator, or a memory location with a register, or it can be used indirect addressing, where of course it is restricted to 256 bytes of memory, because you are using 8-bit registers, and you can not only exchange byte of data, but you can exchange the lower order nibbles. So lower order nibbles can be exchanged. The last instruction that we shall discuss today, last type of data transfer instruction, that is your address object transfer. So in this case, you have got only one instruction, and data pointer can be loaded with some immediate data which is of 16, 2 byte data byte. So data pointer can be initialized with some value by using this instruction. That's why it is being called address object transfer. So you are transferring the object to the data pointer, and subsequently data pointer can be used as an index register for different types of data transfer. So with this we conclude today's lecture, and we have discussed the data types, the instruction format, and particularly the data transfer instructions of 8051. In the next lecture, we shall discuss various types of logical and arithmetic instructions, and also the control transfer instructions, with the help of which you can perform conditional and unconditional jump, subroutine call, return, and so on. Thank you.